Take a slow, deep breath, feeling the air cool as it enters your lungs, and let your body sink deeply into the softness beneath you. Allow your muscles to release their hold, surrendering to the quiet gravity of the moment as we begin our journey into the silent, monumental world of the high latitudes. Glaciers are not merely static blocks of frozen water. They are dynamic, massive rivers of ice that hold nearly 69% of the world's fresh water. What is fascinating is that these giants are in a state of constant rhythmic motion, a phenomenon scientists call the slow dance, where gravity pulls millions of tons of ice down mountain slopes at speeds ranging from a few centimeters to several meters per day. As we settle into this space, imagine yourself standing at the edge of a great ice field, where the air is so crisp it feels like silk against your skin, and the only sound is the subtle, ancient heartbeat of the ice itself. The journey of a glacier begins with a single delicate snowflake falling upon a high mountain plateau. When more snow falls than melts during the summer months, a transformation begins, turning light, airy crystals into a substance called neve. Neve is a granular, partially compacted snow that has survived at least one season of melting. It feels like coarse, wet sand between the fingers. As the years pass and the weight of new layers accumulates, the neve is buried and compressed further into firn. Firn is an intermediate stage between snow and glacial ice, possessing a density of about 400 to 830 kilograms per cubic meter. You can imagine the texture of firn as a dense, crystalline sponge, where the air spaces between the flakes are slowly being squeezed shut by the sheer, relentless weight of time. Eventually, when the snow reaches a depth of about 50 meters, the pressure becomes so great that the air bubbles are sealed off, and the firn recrystallizes into true glacial ice. This ice is remarkably dense, reaching about 917 kilograms per cubic meter. At this stage, the ice becomes a mineral, technically a metamorphic rock, as it undergoes structural changes under pressure. Here, something extraordinary happens to the light. While ordinary snow reflects all wavelengths of light and appears white, the dense crystalline structure of glacial ice absorbs the red and yellow ends of the light spectrum. The short-wave blue light, however, is scattered and reflected back to your eyes. This is why, when you look into the deep fissures of a glacier, you see a color so intense and ethereal, it is known as glacial blue, a hue that feels cool to the touch and deep enough to drown in. As we observe this vast expanse, we must realize that the glacier is moving beneath us. This movement occurs through two primary processes: internal deformation and basal sliding. Internal deformation, or creep, happens because the ice acts like a plastic viscous fluid. Under the massive weight of the upper layers, the ice crystals in the lower depths actually change shape and slide past one another, much like cold honey flowing down a spoon. At the same time, basal sliding occurs when a thin layer of meltwater at the base of the glacier acts as a lubricant. This water, often under high pressure, reduces the friction between the ice and the bedrock, allowing the entire mass, sometimes kilometers thick, to glide slowly over the Earth's crust. If you were to press your ear against the surface of the ice, you would hear the voice of the glacier. It is a symphony of low-frequency groans and sharp, crystalline pops. One of the most enchanting sounds is what scientists call Bergy seltzer. As the ice melts, it releases air bubbles that have been trapped for tens of thousands of years. These bubbles were compressed under enormous pressure when the ice was formed, and as they escape into the water or air, they pop with a distinct fizzing sound. You are literally hearing the atmosphere of the ancient past, the very air that breathed through the world long before the first cities were built. The scale of these ice masses is difficult to comprehend, yet it is deeply grounding. Consider the Lambert Glacier in East Antarctica. It is the largest glacier in the world, stretching over 400 kilometers in length and 100 kilometers in width. It drains about 8% of the Antarctic ice sheet. To stand upon it is to stand upon a slow-moving continent of frost. The thickness of the ice in parts of Antarctica can reach up to 4.8 kilometers, nearly 3 miles of solid frozen history stacked toward the sky. The weight of this ice is so immense that it actually depresses the Earth's crust, pushing it down into the mantle in a process called isostatic depression. When the ice eventually melts, the land very slowly rises back up, a movement known as isostatic rebound, which can continue for thousands of years. Despite the cold, the glacier is a cradle for specialized life. If you look closely at the surface during the twilight hours, you might find the ice worm, Mesenchytreus solifugus. These tiny thread-like creatures are about 2 centimeters long and are among the only animals known to spend their entire life cycle in glacial ice. They feed on snow algae and pollen that blows onto the surface. Curiously, ice worms are so adapted to the cold that if they are warmed to even room temperature, their bodies literally liquefy and dissolve. They represent the ultimate stillness of the glacier, living at the very edge of biological possibility. In the height of summer, you might also see patches of watermelon snow. This is caused by Chlamydomonas nivalis, a species of green algae that contains a secondary red carotenoid pigment to protect itself from intense ultraviolet radiation. As you walk near these patches, you might notice a faint sweet scent reminiscent of fresh watermelon. The red color darkens the snow, causing it to absorb more heat and melt slightly faster, creating a tiny self-sustaining micro-ecosystem of moisture and light. The texture of the landscape surrounding the glacier tells the story of its journey. As the ice moves, it grinds the rock beneath it into a fine, silty powder known as glacial flour or rock flour. These particles are so small, often less than 0.002 millimeters in diameter, that they remain suspended in meltwater lakes. When sunlight hits these lakes, the suspended flour scatters the light, creating a vivid, opaque turquoise or milky green color that looks almost like paint. The tactile sensation of this flour is like the finest velvet, a testament to the glacier's power to crush even the hardest granite into softness. As the glacier flows over the bedrock, it also leaves behind physical records of its passage called striations. These are long, parallel grooves carved into the stone by hard rocks embedded in the base of the moving ice. To run your hand over these striations is to feel the direction of the glacier's historical flow, a tactile map of a journey that took centuries to complete. Sometimes, the glacier carries massive boulders, known as glacial erratics, for hundreds of miles before depositing them in a landscape where they do not geologically belong. These lonely stones, sitting in the middle of a field or perched on a ridge, are the silent travelers of the Ice Age. Near the surface of the glacier, the ice is brittle because there is not enough pressure to make it plastic. This leads to the formation of crevasses, deep, yawning cracks that can reach down to 50 meters before the ice becomes too soft for a crack to exist. The walls of these crevasses are a masterclass in the physics of light, shimmering with shades of indigo and violet, cold and silent. Looking down into one, you are seeing the internal anatomy of the glacier, the layered history of centuries of snowfall, each line representing a winter of the past. The rhythm of the glacier is tied to the concept of glacial mass balance. This is the difference between accumulation, the snow added to the top, and ablation, the ice lost through melting or calving. It is a slow seasonal breathing process. In the winter, the glacier inhales, growing heavy with new snow. In the summer, it exhales, releasing meltwater that feeds the world's great rivers. This balance is a delicate equilibrium, a constant negotiation between the cold of the poles and the warmth of the sun. When a glacier reaches the sea, it experiences calving, where massive chunks of ice break off to become icebergs. But even this is a slow, majestic process, because the density of ice is about 90% of the density of seawater. Approximately 90% of an iceberg's mass remains hidden beneath the surface. This is why icebergs are so stable as they float, drifting on deep ocean currents at a leisurely pace. They are like floating cathedrals of ancient atmosphere, wandering through the salt water. The thermal properties of ice are equally fascinating. Ice has a high latent heat of fusion, meaning it requires a significant amount of energy to change from a solid to a liquid. This thermal inertia is why glaciers act as the world's air conditioners, regulating the global climate by reflecting sunlight back into space and keeping the surrounding air and water cool. As you imagine the glacier, feel that coolness radiating outward, a vast, stabilizing presence that anchors the temperature of the entire planet. In the quiet of this frozen world, time seems to stretch. A single drop of water, frozen into the heart of the Antarctic ice sheet, might take 100,000 years to travel from the center of the continent to the coast. This is a timescale that invites us to slow our own heartbeats, to match the pace of the creeping ice. There is no rush here. There is only the steady, inevitable flow of crystalline structures, the soft hiss of escaping air, and the monumental weight of the blue ice. As we finish this first part of our journey, feel the immense stability of the ice beneath you. You are cradled by a process that began long before you were born and will continue long after. The glacier moves with a purpose that is both powerful and peaceful, a slow dance of molecules and light. Feel the temperature of your surroundings, a gentle, refreshing chill that encourages you to snuggle deeper into your warmth, feeling safe, grounded, and infinitely still. The ice is moving, but you are at rest, held in the frozen memory of the earth. Consider the way our ancestors first looked upon these frozen monoliths, with a mixture of reverence and bewilderment. In the late 18th century, a Swiss aristocrat named Horace Benedict de Saussure became one of the first to systematically study these high-altitude landscapes, eventually offering a reward to the first person who could summit Mont Blanc in 1786. At that time, local alpine communities believed glaciers were sentient beings that could grow or shrink to punish or reward those living in the valleys below. They noticed that the ice was never in the same place twice, observing how massive boulders, known as glacial erratics, appeared in the middle of lush meadows as if dropped by giants. What they were witnessing was the slow, inexorable conveyor belt of the ice, which can transport a house-sized block of granite hundreds of kilometers over several centuries. In the year 1837, a young naturalist named Louis Agassiz shook the scientific world by proposing that Earth had once been gripped by a great ice age. Before this, most scholars believed that the scattered boulders and gouged landscapes of Europe were the result of a massive ancient flood. Agassiz, however, spent his summers living in a primitive hut on the Aar Glacier in Switzerland, where he measured the movement of the ice by driving a line of stakes across its surface. Over several seasons, he watched as the straight line curved into a bow, proving that the center of the glacier moved faster than its edges, just like a liquid river, reaching speeds of roughly 100 meters per year. This discovery transformed our understanding of the planet, revealing that ice is not a static state, but a sculptor that reshapes the very crust of the Earth. Picture this. As the ice slowly retreats in our modern era, it acts as a gentle time capsule, revealing secrets that have been held in a deep freeze for millennia. In 1991, hikers in the Ötztal Alps discovered Ötzi, a remarkably preserved man who lived roughly 5,300 years ago during the Copper Age. Because he was encased in glacial ice shortly after his passing, his skin, clothing, and even the medicinal fungi he carried remained intact for over 50 centuries. The preservation is so perfect that researchers were able to identify his last meal, dried ibex meat and grain, and note the 61 tattoos on his body, which are thought to have been a form of early acupuncture. This demonstrates how the glacier functions as a sterile, oxygen-free vault, protecting organic matter from the typical processes of decay that happen in warmer, lower elevations. Deep within the heart of the ice sheets, we find a record of the Earth's atmosphere that stretches back even further than human history. Scientists use hollow drills to extract cylinders of ice, called ice cores, which can be over 3,000 meters long. Notice how these cores contain tiny pressurized bubbles of air, ancient gasps of the planet's breath, trapped during the time of the Roman Empire, the building of the pyramids, or even the last interglacial period, 130,000 years ago. By analyzing the ratio of oxygen-18 to oxygen-16 isotopes within these bubbles, researchers can determine the exact temperature of the Earth at the moment that specific layer of snow fell. It is a tactile, frozen library where every centimeter of ice represents a page of history. Documenting volcanic eruptions through layers of sulfuric acid and tracking the rise and fall of ancient civilizations through traces of lead and copper dust. At this very moment, as you settle into your rest, consider the microscopic world thriving on the surface of the ice, a phenomenon known as cryoconite. If you were to look closely at a glacier's surface, you would see small cylindrical pits filled with dark, silty water. These are cryoconite holes, formed when wind-blown dust, composed of soot, rock particles, and microbes, settles on the ice. Because this dark material has a lower albedo than the surrounding white snow, it absorbs more solar radiation, melting its way vertically down into the glacier. Inside these miniature sapphire-walled wells, an entire ecosystem flourishes. You might find tardigrades, also known as water bears, which are 8-legged microanimals less than a millimeter long. These resilient creatures can survive being frozen to nearly absolute zero or heated to 150 degrees Celsius by entering a state of cryptobiosis, where their metabolism slows to 0.01% of its normal rate, waiting for the ice to soften. The texture of the ice also reveals the passage of the seasons through features called Forbes bands, or ogives. As you look down at a glacier from a distance, you might see a series of alternating dark and light-curved bands that look like ripples in a pond. Each pair of bands represents 1 year of the glacier's life. The light bands are formed in the winter, when fresh, clean snow accumulates in the high-altitude basins. The dark bands are formed in the summer, when the ice surface melts and collects dust, pollen, and debris as it flows over a steep icefall. These bands act like the rings of a tree, marking the steady, rhythmic pulse of the glacier's growth as it descends from the peaks toward the valley floor at a pace that might only be a few centimeters every hour. Researchers have noted that glaciers possess a unique thermal signature. Even in the height of summer, the internal temperature of a cold-based glacier, typical of Antarctica, remains well below freezing, often hovering around 20 or 30 degrees Celsius. However, temperate glaciers, like those found in the Alps or the Cascades, stay right at the melting point throughout their entire mass. This allows liquid water to exist within the ice, creating a network of internal plumbing called moulins. A moulin is a vertical shaft, sometimes several meters wide, where surface meltwater plunges deep into the glacier's interior. Imagine the sound of this water, a hollow, echoing roar that vibrates through the very soles of your feet as the liquid carves smooth, scalloped tunnels through the blue ice, eventually emerging at the glacier's toe as a subglacial stream. What is happening now is a process of mineral enrichment. As the glacier grinds against the bedrock with a pressure of over 10,000 pounds per square foot, it pulverizes the stone into glacial milk. This liquid is rich in minerals like potassium, phosphorus, and calcium. When this mineral-heavy water flows into the ocean, it triggers massive blooms of phytoplankton, microscopic marine plants that form the base of the entire oceanic food web. A single glacier can provide the nutrients necessary to support thousands of tons of krill, which in turn sustain the gentle migration of humpback whales. The glacier, though frozen, is a fountain of life, pumping essential chemistry into the world's ecosystems with every drop of its meltwater. As we observe the frozen record, we can see evidence of the Little Ice Age, a period of cooling that lasted from approximately 1300 to 1850 AD. During this time, glaciers in the northern hemisphere expanded significantly, swallowing up mountain farms and forcing villagers to move. In London, the River Thames froze so solidly that frost fairs were held on the ice, with shops and even pubs set up on the frozen surface. The ice of this era is still present in many glaciers today. It is denser and more compact, a physical memory of a time when the world was just a few degrees cooler. To touch this ice is to touch the same climate that inspired the somber, snowy landscapes in the paintings of the Dutch masters. Notice the sheer weight of this history as it presses down, creating a sense of profound stillness. In certain parts of the world, like the high peaks of the Andes, glaciers are the only source of water for millions of people during the dry season. The indigenous Quechua people have long understood this, referring to the glaciers as apu, or mountain spirits, that protect the flow of life. They recognize that the ice is a living reservoir, a battery that stores the winter's energy and releases it slowly when the sun is at its strongest. This relationship is a delicate dance of timing and temperature, ensuring that the valleys below remain green, even when the rains fail to arrive. Think of the glacier not as a block of ice, but as a slow-motion fluid. Its viscosity is such that it flows roughly 100,000 times more slowly than liquid water. This creates incredible internal tension. Near the edges, where the ice rubs against the valley walls, the friction slows the flow, while the center rushes forward. This differential speed creates marginal crevasses, which always point upstream at a 45-degree angle. By looking at the orientation of these cracks, an experienced glaciologist can read the history of the glacier's movement, like a sailor reads the waves of the sea. In the quiet of this narrative, imagine the scent of the glacial environment. It is not the scent of pine or earth, but the smell of total purity, the scent of old water. It is a crisp, metallic aroma, like the smell of a cold stone pulled from a deep well. There is a complete absence of the organic sense of decay or heat. It is the smell of the world at its most fundamental, a clean slate of frozen H2O. As you breathe in, feel that purity entering your own space, cooling your thoughts and slowing your mind to the pace of the ice. We are now deep within the observation of this giant's life cycle. We have seen how it preserves the past, how it supports life in its smallest forms, and how it nourishes the planet on a global scale. The glacier is a monument to patience. It does not hurry to reach the sea. It moves with the confidence of something that knows it has all the time in the world. As you continue to rest, let that sense of geological time settle over you. There is no need for haste. There is only the steady, rhythmic movement of the ice, the gentle pressure of the atmosphere, and the deep, enduring silence of the high mountains. You are part of this rhythm now, moving slowly, peacefully, toward a state of total frozen tranquility. Imagine for a moment a simple ice cube from your kitchen freezer. It is cloudy, white, and full of tiny imperfections. Those clouds are actually microscopic bubbles of air, trapped when the water froze quickly. Now, compare that to a fragment of ancient glacial ice. Because the glacier is formed under the immense weight of hundreds of meters of snow, those air bubbles are squeezed so tightly that they eventually dissolve into the crystal structure itself, or are expelled entirely. This results in ice that is significantly more dense than anything you can produce at home, often possessing a clarity that rivals the finest lead crystal. It is this extreme density that allows the ice to behave like a prism, filtering the light until only the most tranquil, deep blues remain. What's actually occurring beneath the surface of these giants is a process similar to how a memory foam mattress reacts to your body weight. This is known as isostasy. When a massive glacier, like the Vatnajökull in Iceland, sits upon the Earth's crust, its weight is so profound, reaching an average thickness of 400 meters, that it actually pushes the tectonic plate down into the softer mantle below. Scientists have calculated that for every 3 meters of ice added to a glacier, the Earth's crust sinks about 1 meter. When you step off a memory foam mattress, it slowly regains its shape. Similarly, when a glacier melts, the land beneath it begins a post-glacial rebound, rising upward at a rate of about 1 centimeter per year in some parts of Scandinavia. This is a planetary scale version of the gentle rise and fall of your own chest as you breathe. To understand the speed of a glacier, it helps to look at the garden snail. While we think of glaciers as static, they are surprisingly mobile. The Jakobshavn Isbrae in Greenland is one of the fastest moving glaciers on the planet, sometimes advancing at a rate of 45 meters per day. This is roughly 1.8 meters per hour. If you were to sit very still and watch a specific point on its surface, its movement would be nearly 4 times faster than the average speed of a garden snail, which moves at about 0.5 meters per hour. This gallop, as glaciologists call it, is a rhythmic, constant push toward the sea, driven by the sheer mass of the ice sheet behind it. Consider the way a master chef uses a fine sifter to create the perfect flour. The glacier does something nearly identical on a gargantuan scale. As the ice slides over the valley floor, it acts like a giant piece of sandpaper. It doesn't just scratch the rock, it pulverizes it into particles smaller than 0.002 millimeters. This glacial flour is so fine that it feels like silk or velvet between your fingers. Interestingly, because these particles are so light, they don't sink when they reach a lake. Instead, they stay suspended in the water, scattering sunlight and giving glacial lakes their famous opaque turquoise color. It is as if the glacier is slowly painting the landscape with the minerals it has harvested from the mountains. What is happening deep at the base of the ice is a phenomenon known as pressure melting. Think of how a professional ice skater glides effortlessly across a rink. The thin blade of the skate concentrates the skater's weight into a tiny area, which creates enough pressure to momentarily melt a microscopic layer of ice, providing a lubricant. A glacier does this on a much larger scale. At the bottom of a glacier that is 2 kilometers thick, the pressure is so intense that the melting point of the ice actually drops below 0 degrees Celsius. This creates a thin, slippery film of water that allows the entire mountain of ice to slide forward, a process called basal slip. This hidden layer of water acts as the glacier's own set of skates, facilitating its long, slow journey down the slope. Notably, the glacier also acts like a pair of giant tweezers in a process called plucking. As the ice melts and refreezes around cracks in the bedrock, it literally grabs hold of massive chunks of stone. When the glacier moves forward, it plucks these stones, some the size of small cars, right out of the ground and carries them along. This is why you will often find glacial erratics, which are large boulders sitting in the middle of fields where they don't geologically belong. It's like finding a stray puzzle piece in the wrong box. The glacier is the silent mover that transported that piece across hundreds of miles of terrain over thousands of years. Think of the glacier's structure as a multi-story building. The top 50 meters are the brittle zone, where the ice is cold and hard, prone to cracking into deep crevasses. Below that, however, the pressure becomes so great that the ice enters the plastic zone. In this lower section, the ice no longer cracks. Instead, it flows like warm wax or thick molasses. This duality, hard on top, soft and flowing underneath, is what allows the glacier to navigate around bends in a valley without shattering. It is a lesson in flexibility and strength, showing how even the hardest substance can learn to flow when the weight of the world is upon it. Observe the similarity between a glacier and a highly efficient solar mirror. This is measured by albedo, which is the reflectivity of a surface. Fresh glacial snow has an albedo of about 0.9, meaning it reflects 90% of the sun's energy back into space. In comparison, dark ocean water has an albedo of only about 0.06, absorbing most of the heat it receives. By maintaining this high albedo, glaciers act as the Earth's natural cooling system, much like wearing a white t-shirt on a scorching summer day to stay refreshed. This reflection of light is a quiet, constant service the ice performs for the planet, keeping the atmosphere at a stable, livable temperature. Deep within the Antarctic ice, there are hidden worlds that we are only just beginning to understand. Scientists have discovered over 400 subglacial lakes, the largest of which is Lake Vostok. Imagine a body of water the size of Lake Ontario, buried under 4 kilometers of solid ice. This lake has been sealed off from the rest of the world for perhaps 15 million years. It is a secret basement under the massive house of the ice sheet, kept liquid not by the sun, but by the warmth of the Earth's core and the insulating blanket of the ice above. Within these dark, high-pressure waters, researchers have found evidence of specialized bacteria that thrive on minerals alone, proving that life finds a way to persist in even the most silent and secluded corners of our world. The transition from snow to ice is a slow, methodical compression that glaciologists call fernification. It takes about 10 feet of fresh, fluffy snow to eventually create just 1 foot of dense glacial ice. It is a process of extreme patience, where each layer of winter snow is gradually stripped of its air and space until it becomes a singular, unified mass. This is much like how you might compress a large down pillow to fit it into a small travel bag. The substance remains the same, but its nature changes from airy and light to firm and supportive. If you were to look at the very front of the glacier, known as the terminus, or the snout, you would see the result of a process called ablation. This is the exhalation of the glacier, where ice is lost through melting, evaporation, or calving into the sea. At the same time, high up in the mountains, the accumulation zone is where the glacier inhales new snow. Between these two areas lies the equilibrium line, a perfect point of balance where the amount of snow gained exactly matches the amount of ice lost. This line is the glacier's pulse, moving up and down the mountain with the changing climate, a visual representation of the Earth's metabolic health. In certain parts of the world, glaciers create nunataks, which is a Greenlandic word for lonely peaks. These are the jagged tops of mountains that stick out above the surface of the ice sheet. A nunatak is like a desert island in a frozen sea, a tiny sanctuary of rock where hardy lichens and mosses can grow, surrounded by thousands of square miles of moving ice. These isolated spots of life remind us that even in the most monolithic environments, there is diversity and resilience. At this very moment, nearly 75% of the Earth's fresh water is held within these frozen reservoirs. If all the glaciers on Earth were to melt simultaneously, the global sea level would rise by approximately 70 meters, or about 230 feet. This fact illustrates the incredible volume of these structures. They are the planet's primary water towers, holding the lifeblood of our ecosystems in a stable, frozen state. They release this water with incredible timing, providing a steady flow to rivers during the hottest, driest months of the year when other water sources have vanished. As you continue to settle into your rest, think about the seracs. These are giant blocks or columns of ice, often the size of houses, that form when a glacier flows over a steep cliff. They stand like frozen sentinels, leaning against one another in a state of precarious but beautiful balance. They represent the internal architecture of the glacier, a complex arrangement of stress and support that has been refined over centuries. The sound of the glacier is also a point of interest. Beyond the Bergy seltzer bubbles popping, there is the cryoseism, or icequake. These are not like traditional earthquakes. They are gentle, localized vibrations caused by the ice shifting or water moving through internal channels. To a listener, they might sound like the distant muffled thump of a heartbeat or the soft creak of an old wooden floor. It is the sound of the earth adjusting its weight, finding a more comfortable position in the cradle of the mountain valley. We have explored how the glacier acts as a mirror, a sculptor, a time capsule, and a fountain. It is a system of immense complexity that operates with total, unhurried simplicity. It follows the laws of physics with a graceful, heavy elegance. As you lie there, feel the weight of your own body as a grounding force, much like the weight of the ice. Let your breathing become as rhythmic and reliable as the advance of the glacier. You are safe. You are supported, and you are part of a world that values the slow, steady progress of time. There is no need to rush into tomorrow. Like the ice, you can simply exist in this state of quiet, powerful transition, moving toward the sea of sleep at your own perfect, natural pace. Think of the glacier not as a silent observer, but as a master weaver, drawing together the threads of the sky, the mountains, and the deep sea into a single cohesive tapestry of life. What's truly remarkable is that this massive frozen entity supports mobile communities on its very back, such as the glacier mice. These are not rodents, but oval-shaped cushions of moss, often of the genus Grimmia, that develop around a small stone or piece of debris. Over several years, these mossballs grow to be about the size of a grapefruit. Because they are not attached to the ground, they must roll to survive, ensuring each side receives equal sunlight for photosynthesis. Researchers tracking these mossballs have found that they actually move in a synchronized fashion, like a slow-motion herd of soft green velvet spheres wandering across the white ice at a rate of about 1 inch per day. It is a miniature world of biological coordination occurring in one of the most extreme environments on the planet. As we look at the larger landscape, notice how the glacier functions as a planetary scale conveyor belt for nutrients. Deep within the ice, the grinding of rock produces specific minerals like magnetite and hematite, which are rich in bioavailable iron. When the glacier eventually meets the coastline and releases its meltwater, it acts as a colossal fertilizer for the surrounding ocean. Scientists have discovered that this iron-rich dust, or glacial flour, can trigger massive blooms of marine phytoplankton over areas covering thousands of square kilometers. These tiny organisms are the primary producers of the ocean, capturing carbon dioxide and releasing nearly 50% of the oxygen we breathe. Every deep, restorative breath you take right now is connected to the slow, heavy grinding of ice against granite, thousands of miles away. At this very moment, consider the way the glacier interacts with the bedrock to create unique geological formations. Have you ever seen a roche moutonnée? This is a French term meaning sheep-back rock. It describes a piece of bedrock that has been sculpted by the passing ice into a smooth, asymmetrical mound. One side is polished to a glass-like finish by the pressure and abrasion of the glacier, while the other side is jagged and steep, where the ice has plucked away chunks of stone. Walking across these rocks feels like touching the physical signature of the Earth's history. You can feel the smooth, cool surface, where the ice once glided with the weight of a mountain, and the rough edges where it asserted its immense power. What is happening now is a transformation of the Earth's surface through the creation of eskers. Deep beneath the ice sheet, subglacial rivers flow through tunnels carved into the frozen base. These rivers carry enormous amounts of gravel and sand. When the glacier finally retreats, it leaves behind the sediment that was trapped in those tunnels, forming long, winding ridges that can stretch for hundreds of kilometers across the land. These eskers look like giant, slumbering snakes made of stone, providing elevated, well-drained pathways that Arctic animals like caribou and wolves use to navigate the marshy tundra. The glacier, in its passing, creates the very infrastructure that terrestrial life uses to thrive. Notice the way the glacier archives time in annual layers, similar to the varves found in glacial lakes. A varve is a pair of sediment layers deposited in a single year. In the summer, the rapid melting of the glacier carries coarse, light-colored sand into the lake. In the winter, when the lake surface freezes and the water becomes still, fine, dark-colored clay settles to the bottom. By counting these pairs, geologists can read the history of a glacier's health over thousands of years, much like reading the barcode on a product in a shop. Each layer is a testament to a specific summer's warmth and a specific winter's chill, a precise and rhythmic ledger of the planet's pulse. Scientists discovered that the entire cycle of these glaciers is governed by the Milankovitch cycles, long-term variations in the Earth's orbit. Every 100,000 years, the shape of the Earth's orbit, known as eccentricity, shifts from being nearly circular to slightly elliptical. This, combined with the wobble of the Earth's axis, or precession, determines how much solar energy reaches the poles. We are currently living in an interglacial period, a brief, warm exhale in a cycle that has seen at least 20 major glacial advances over the last 2.6 million years. Realizing this helps us see the glacier not as a disappearing relic, but as a recurring character in the epic story of our planet, a periodic visitor that comes to refresh and reshape the world. Consider the trim line, a distinct boundary on a mountain valley wall. Above this line, the rock is weathered and covered in old lichens. Below it, the rock is smooth, bare, and fresh. This line marks the highest point the glacier reached during its last advance. It is a visual high water mark of the ice, showing us that the valley we are observing was once filled to the brim with a solid flowing river of blue. This perspective allows us to understand that the landscape is not permanent, but is in a constant state of being molded, like a piece of clay in the hands of a very patient artist. Picture the way life finds sanctuary in glacial refugia. During the height of the last ice age, when much of the northern hemisphere was covered in a sheet of ice 2 miles thick, certain pockets of land remained ice-free. These were often high mountain ridges or coastal strips where the climate remained just mild enough for plants and animals to survive. It was in these tiny protected havens that species like the Arctic poppy and various types of mountain spiders waited out the millennia. Once the ice began its slow retreat, these species marched back out to recolonize the barren land. The glacier, while dominant, always leaves room for the persistence of life, acting as a steward of biodiversity by forcing species to adapt and find new ways to endure. Deep within the ice, there is a physical phenomenon called plastic flow. Most substances are either solid or liquid, but glacial ice exists in a beautiful middle ground. Under the pressure of its own weight, which can exceed 350 pounds per square inch at the base, the ice crystals rearrange their molecular structure. They flatten and slide over one another like a deck of playing cards. This internal movement is so smooth that it produces no heat from friction, allowing the glacier to remain at a stable, frozen temperature, even as it travels miles from its origin. This fluid-like grace in a solid body is a reminder that we, too, can find ways to move through the pressures of life with a steady internal flexibility. Scientists have also identified cryoconite as a significant factor in the glacier's ecology. As mentioned, these dark dust particles create small holes in the ice. But what is fascinating is the specific composition of this dust. It often contains soot from distant forest fires or even stardust, micrometeorites that have fallen from space and been concentrated by the melting ice. When you look at a glacier, you are looking at a collection of the Earth's atmosphere, the forest's history, and the galaxy's debris, all held together in a crystalline embrace. What's happening at the edges of the glacier is a process of isostatic adjustment, which we can relate to our own bodies. Just as your bed adjusts to the weight of your body when you lie down, the Earth's lithosphere, the rigid outer shell, actually flexes. In places like Hudson Bay, the land is still rising by about 1.2 centimeters a year because the weight of the massive Laurentide ice sheet was removed 10,000 years ago. This rebound is a slow, grounding movement, a planetary sigh of relief that reminds us that everything eventually returns to a state of balance. In your own life, you might feel the pressure of time or the weight of responsibilities. Relate this to the confining pressure that turns snow into ice. That pressure doesn't destroy the snowflake. It transforms it into something more durable, more beautiful, and more capable of shaping the world. The glacier is a symbol of the strength that comes from duration. It does not achieve its goals through speed, but through the relentless application of its own nature. It teaches us that there is profound power in the slow, the steady, and the consistent. Notice the sound of glacial flour being ground. While we cannot hear a single particle, the collective grinding of millions of tons of ice over stone produces a low-frequency vibration known as ice hum. This sound is often below the range of human hearing, but it can be picked up by sensitive seismometers. It is a deep, subsonic lullaby that resonates through the crust of the Earth, a constant reminder of the planet's ongoing labor. As you listen to the silence of your own room, imagine that deep hum beneath you, a steady foundation of movement that supports the stillness of your rest. The density of this ice, 917 kilograms per cubic meter, is just enough to make it float in seawater, which has a density of about 10^125 kilograms per cubic meter. This small difference is what creates the iconic sight of icebergs. Because they are so close in density, icebergs are incredibly sensitive to the currents of the ocean. They don't just drift, they follow the deep water highways of the planet, traveling from the poles toward the equator, slowly cooling the tropical waters and maintaining the global thermal balance. As we conclude this part of our journey, feel the interconnection between the frozen peaks and the deep blue sea. You are not an isolated observer. You are part of this grand circulating system of water and energy. The ice is moving, the land is rebounding, and the oceans are being nourished. Everything is working in a slow, rhythmic harmony. Let the coolness of the glacier enter your mind, clearing away the clutter of the day and replacing it with the vast blue clarity of ancient ice. You are safe. You are part of a magnificent process, and you are ready to descend further into the quiet, frozen depths of your own rest. Consider the specific physics of light as it interacts with the crystalline lattice of the ice. What is chemically impressive is that glacial ice is actually classified as a monomineralic metamorphic rock. Unlike the ice in a frozen puddle, which is often riddled with air and cracks that reflect all wavelengths of light equally, glacial ice has been compressed for so long that the air bubbles are forced out. This creates a dense, uniform structure where the water molecules are arranged in a hexagonal crystal system. When sunlight enters this dense medium, the hydrogen-oxygen bonds in the water molecules absorb the longer wavelengths of the spectrum, the reds and yellows. The shorter, high-energy blue wavelengths are scattered through the crystal lattice and reflected back to your eyes. This is why the heart of a crevasse glows with a saturated electric sapphire color that seems to emanate from within the ice itself. At this very moment, as you envision this blue radiance, notice the temperature differential. Glaciers possess an incredible amount of thermal inertia. Because they are so massive, they do not respond to the daily fluctuations of the sun. Even on a warm afternoon, the core of the glacier remains a steady, rhythmic cold. This is due to the latent heat of fusion, a scientific principle stating that it takes a massive amount of energy, 334 joules per gram, just to turn ice into water without even raising its temperature. The glacier acts as the Earth's slow-acting heat sink, a stabilizing force that absorbs heat from the atmosphere while remaining steadfastly frozen. It is a planetary-scale ice pack, cooling the air around it and creating its own local microclimate of calm, refreshing stillness. Scientists discovered that the surface of the glacier is not a flat plain, but a textured landscape of sun cups. These are bowl-shaped depressions, often ranging from a few centimeters to over a meter in depth, formed by the differential melting of the ice. When a small piece of dark dust or a leaf lands on the snow, it absorbs more heat and melts a tiny hole. Once a small depression forms, it begins to act like a parabolic mirror, concentrating solar radiation into the center of the cup and causing it to deepen. Walking across a field of sun cups feels like navigating a giant frozen honeycomb, where the edges are sharp and crystalline, while the interiors are smooth and watery. This texture is a physical record of the sun's daily path across the sky, carved into the very skin of the mountain. What is happening now is an auditory phenomenon called ice singing. While we often think of the Arctic as silent, glaciers are actually quite vocal. As the ice flows over uneven bedrock, internal stresses build up until the ice reaches its shear strength, the point where it must shift to relieve the pressure. This results in microfractures that emit high-frequency acoustic signals. If you were to place a hydrophone in a glacial lagoon, you would hear a constant musical tinkling, like thousands of tiny glass bells. This is caused by the release of air bubbles that have been trapped under pressures of up to 20 atmospheres. When the ice melts, these pressurized bubbles burst with a distinctive pop, a process called effervescence that is the sound of the ancient atmosphere finally being set free after 50,000 years of captivity. Deep within the ice, the pressure can become so intense that it creates a substance known as blue ice. This ice has a density of about 9 to 17 kilograms per cubic meter, which is nearly the maximum density possible for frozen water. Because there are almost no air bubbles to scatter the light, the ice is as clear as a polished diamond. In certain areas of Antarctica, wind-scoured blue ice areas are so smooth and hard that they are used as natural runways for heavy cargo planes. To touch this ice is to touch a surface that is nearly frictionless, a texture that feels more like cold metal or glass than the snow we are familiar with. Picture this. The glacier is also an olfactory environment. The air surrounding a glacier is some of the purest on Earth, often containing fewer than 10 particles per cubic centimeter. This absence of dust, pollen, and organic pollutants creates a scent that is best described as sharp. It is the smell of ozone and negative ions produced by the movement of the ice and the rushing of meltwater. There is a crispness to the air that feels like it is cleaning your senses, a metallic mineral scent that is the polar opposite of the heavy, humid smells of a forest. It is the scent of the world's beginning, elemental, fresh, and profoundly still. Notice how the glacier interacts with the water at its grounding line. This is the specific point where the glacier leaves the bedrock and begins to float on the ocean. At this junction, the ice is subjected to the rhythmic rise and fall of the tides. This creates a tidal flex, where the ice bends and groans with every cycle of the moon. Scientists use tilt meters to measure this movement, which can be as much as a few meters every 12 hours. This is the glacier's most intimate connection to the rest of the planet. The way the gravity of the moon pulls on the ice, causing the massive sheet to breathe in and out in synchronization with the world's oceans. What's happening at the microscopic level is a fascinating biological adaptation. You might see patches of red snow, often called watermelon snow, which is caused by the green alga Chlamydomonas nivalis. What is scientifically curious is that this alga is actually green, but it produces a bright red carotenoid pigment called astaxanthin to protect its chlorophyll from the intense ultraviolet radiation at high altitudes. This pigment acts like a natural sunscreen, absorbing the harsh UV rays and converting them into heat. This heat slightly melts the surrounding ice, providing the alga with the liquid water it needs to survive. It is a self-sustaining cycle where the life form creates its own tiny warm oasis in the middle of a frozen desert. Consider the cryosphere, the portion of the Earth's surface where water is in solid form. Glaciers are the most visible part of this system, but they are supported by a hidden network of permafrost, ground that remains at or below 0 degrees Celsius for at least 2 consecutive years. In many alpine regions, the glacier and the permafrost are inseparable, with the ice acting as an insulating blanket that prevents the ground from thawing. This relationship stabilizes entire mountain ranges. The ice acts as a geological glue, holding loose rocks and scree slopes together. Without the cooling presence of the glacier, these mountains would slowly crumble, showing that the ice is not just a visitor, but a structural foundation of the Earth's topography. At this very moment, the glacier is also producing frazzle ice. In the turbulent meltwater streams at the glacier's toe, the water can become supercooled, colder than 0 degrees Celsius, but still liquid. Small needle-like crystals of ice begin to form in the water column. These crystals, called frazzle ice, are incredibly sticky. They clump together to form anchor ice on the bottom of the stream, or pancake ice on the surface. To watch this happen is to see the very moment that liquid becomes solid, a delicate transition that looks like white lace forming on the surface of the dark, rushing water. Notice the sound of the moulins, the vertical shafts that carry meltwater from the surface to the base of the glacier. As the water falls, it creates a piezometric head, a form of hydraulic pressure. This pressure is so great that it can actually lift the entire glacier by several centimeters, reducing the friction on the bedrock and allowing the ice to surge forward. A surge is a period where a glacier moves at 10 to 100 times its normal speed. This is not a violent event, but a majestic, accelerated glide, a sudden burst of energy in a life usually defined by centuries of patience. The chemical composition of the meltwater is also unique. Because it has been isolated from the atmosphere for so long, glacial meltwater is often alkaline, with a higher pH than rain or river water. This is because the grinding of the rocks releases minerals like calcium carbonate. When this water reaches the sea, it helps to neutralize the acidity of the ocean, acting as a natural buffer. The glacier is a chemist, carefully balancing the pH of the planet's water supply with every drop that melts from its snout. What is happening now is the formation of penitentes. In high altitude, dry environments like the Andes, the sun causes the ice to sublimate, turning directly from a solid into a gas without melting first. This results in the formation of tall, thin blades of hardened snow or ice, sometimes reaching several meters in height, all pointing toward the midday sun. They look like a crowd of white-robed monks standing in silent prayer. This is a sensory experience of extreme aridity and light, where the ice is sculpted not by water, but by the thin, cold air and the relentless solar radiation. Deep within the Antarctic ice sheet, scientists have discovered polynyas, large areas of open water surrounded by sea ice. These are kept open by katabatic winds, which are gravity-driven winds that roll down the slope of the glacier at speeds of up to 100 miles per hour. These winds are incredibly dry and cold, and they push the new ice away from the coast as soon as it forms. These polynyas are biological hotspots, providing a sanctuary for seals and penguins to breathe and hunt in an otherwise frozen ocean. The glacier, through the movement of the air it cools, creates these vital windows of life in the middle of the ice. As we deepen our observation, feel the viscosity of the air, Cold air is denser than warm air, and near a glacier, it feels heavy and thick. When you breathe it in, it feels more substantial, as if you are truly filling your lungs with something tangible. This density carries sound further and more clearly, which is why the distant crack of a calving iceberg can be heard for miles. It is a world of enhanced clarity, where every sound, every scent, and every color is amplified by the cold. We are now standing at the threshold of the final stage of our journey. We have felt the textures of the sun cups, smelled the ozone of the pure air, and heard the singing of the ancient bubbles. The glacier has shown us its internal blue light and its structural strength. It has revealed itself as a chemist, a sculptor, and a foundation. As you rest, let these sensory details merge into a single, cohesive feeling of cold, stable peace. You are like the core of the glacier, unmoved by the fleeting warmth of the day, steady, dense, and full of quiet, crystalline energy. The world is moving slowly around you, but you are anchored in the deep, blue heart of the ice, ready to transition from the physical world into the silent, frozen depths of your own sleep. As our exploration of these frozen giants nears its conclusion, observe the gradual process of primary succession, the way life begins to reclaim the land as a glacier retreats. When the ice edge recedes, it leaves behind a landscape of raw, scoured bedrock and till, a chaotic mixture of boulders, gravel, and glacial flour. This environment is initially sterile, but the transition begins almost immediately with the arrival of biological soil crusts. These crusts are composed of cyanobacteria, lichens, and mosses that can survive on bare rock. They perform the critical first step of nitrogen fixation, pulling nitrogen from the atmosphere and converting it into a form that other plants can eventually use. Specifically, the pioneer species, Dryas octopetala, or mountain avens, often takes root in this rocky debris. This hardy, white-flowered shrub has a symbiotic relationship with nitrogen-fixing bacteria in its root nodules, allowing it to build the very first layers of organic soil in a world that was recently buried under a mile of ice. Notice how the retreating glacier leaves behind terminal moraines, massive, semicircular ridges of debris that mark the glacier's furthest point of advance. These ridges act as natural dams, trapping meltwater to create proglacial lakes. Within these lakes, a distinct process of sedimentation occurs. In the summer months, fast-flowing meltwater carries heavy sand and gravel into the lake, while in the winter, the surface freezes and only the finest clay particles settle to the bottom. This results in the formation of varves, thin, alternating layers of light and dark sediment. By counting these layers, scientists can determine exactly how many years have passed since the ice retreated from that specific location, a geological clock that ticks once per year, documenting the slow, rhythmic transition of the landscape from ice to water. What is happening now? As the weight of the glacier is removed from the Earth's crust, is a phenomenon called isostatic rebound. During the height of the last ice age, the weight of the Fennoscandian ice sheet was so great that it depressed the Earth's crust by nearly 800 to 1,000 meters. Now that the ice is gone, the land is slowly rising back up toward its original position. In parts of the Gulf of Bothnia, the land is currently rising at a rate of approximately 9 millimeters per year. This process is so steady that former sea harbors from the Middle Ages are now located several kilometers inland. It is a slow, planetary-scale unbending, a restorative movement that continues for thousands of years after the ice has vanished, showing that the Earth has a long-term memory of the weight it once carried. Consider the formation of kettle lakes, which occurs when a large block of ice breaks off from the main glacier and becomes buried under a layer of sediment. Because the sediment acts as an insulator, this dead ice can take decades or even centuries to melt. When it finally does, the sediment above it collapses, creating a circular depression that fills with groundwater. These kettle lakes, common across the northern United States and Europe, are often perfectly round and surprisingly deep, a final, lingering gift from the glacier to the local ecosystem. They provide stable, sheltered habitats for aquatic plants and migratory birds, turning a landscape of scars into a network of life-giving sanctuaries. Picture the albedo feedback loop, a critical process in the glacier's life cycle. When snow is fresh and white, it has an albedo of 0.9, reflecting 90% of solar energy back into space. However, as the surface melts, it exposes darker ice or accumulated dust, which has a lower albedo. This darker surface absorbs more heat, which in turn leads to more melting, exposing even more dark surface. This is a step-by-step cycle of thermal absorption that regulates the glacier's mass balance. Yet, in the high Arctic, the arrival of the polar night, which lasts for 182 days at the poles, brings this process to a complete halt. During this time, the glacier enters a state of total dormancy, shedding heat into the vacuum of space and strengthening its crystalline bonds under the starlight. Deep within the glacier's terminus, the process of calving begins. This is not a random breaking of ice, but a calculated response to the forces of buoyancy and gravity. As the glacier flows into the ocean, the water exerts an upward force on the ice. Eventually, the bending stress exceeds the fracture toughness of the ice, and a massive block shears off. Scientists have found that the frequency of calving is often linked to the hydrostatic pressure at the glacier's base. When meltwater levels rise, the pressure at the bottom of the glacier increases, effectively lubricating the ice and pushing it faster toward the sea. This is a hydraulic dance where the presence of liquid water dictates the speed at which the solid ice moves toward its final destination. Notice the way the glacier sorts its cargo. As meltwater streams flow through internal tunnels called eskers, the water's velocity determines which rocks it can carry. Fast-moving water transports large cobbles, while slower water can only carry sand. This results in the creation of long, winding ridges of well-sorted gravel that can stretch for hundreds of miles once the ice melts. These eskers are like the fossilized remains of the glacier's internal plumbing system. They provide essential drainage for the surrounding tundra and serve as elevated highways for wildlife, showing how the glacier's internal processes create the physical foundations for future ecosystems. What's happening at the molecular level during the rounding of snow crystals is a process called destructive metamorphism. When snow first falls, it consists of complex six-pointed stars with high surface area. Over time, water molecules migrate from the tips of the stars to the hollows, seeking a more stable, lower energy shape. The crystals become smaller, rounder, and more tightly packed. This increases the density of the snowpack from about 50 kilograms per cubic meter to over 500 kilograms per cubic meter. This gradual densification is the first step in the centuries-long journey toward becoming glacial ice, a lesson in how shedding complexity can lead to greater strength and longevity. As we bring our observation of the glacier to a gentle, comforting halt, notice the transition in your own environment. The immense, slow movement of the ice is not so different from the rhythm of your own rest. Just as the glacier finds equilibrium Between the snow it gains and the ice it loses, your body is now finding its own balance. The cooling presence of the ice has cleared the air, leaving behind a state of profound, crystalline clarity. The weight of the day is being lifted, much like the weight of the ice lifting from the Earth's crust, allowing you to rise into a state of weightless tranquility. Connect the slow dance of the ice to the slow pulse of your own heart. The glacier does not struggle against gravity. It surrenders to it, flowing with an inevitable grace. You are now surrendering to the gravity of your own bed, feeling the supportive pressure of the mattress beneath you. The silence of the polar night is entering your space, a deep blue and absolute stillness. There is no more movement required. There is only the steady, rhythmic breath of a world at rest. The ancient air, once trapped in the ice, is now the air you breathe, cool, pure, and life-giving. Transition now from the external world of the mountains to the internal world of your dreams. The blue light of the crevasses is softening into a gentle, dark indigo. The sound of the Bergy seltzer bubbles has faded into a quiet white noise that anchors your mind. You are safe in the cradle of the valley, protected by the monumental presence of the ice. The glacier's journey has taken thousands of years, and your own journey into sleep is just as significant, a necessary cycle of renewal and preservation. I am stable, grounded, and at peace. The coolness of the ice brings clarity to my mind. I release the weight of the day and embrace the stillness of the night. My breath is as rhythmic and steady as the falling snow. I am supported by the deep foundations of the earth. I am part of the long, slow cycles of nature. I allow my thoughts to become as quiet as the frozen peaks. I am safe in the blue heart of the winter night. Each breath I take brings a deeper sense of rest. I am drifting into a state of total crystalline calm. The world is at rest, and I am at rest with it. I trust the timing of my own nature. I am surrounded by a blanket of pure, refreshing quiet. I am sinking deeply into the softness of the dark. The ice is still, and I am still. I am moving toward a sleep as deep as the ancient glaciers. My mind is clear, my body is heavy, and my heart is light. I am entering the silent, beautiful world of dreams. The stars are cold and bright, but I am warm and safe. I am one with the slow, eternal dance of the earth. Good night.